You are holding a coin. Look at it. A penny. A dime. Something small enough that your thumb can cover it completely. Now, spin it on a table. Watch how it wobbles at first, how friction slows it down, how eventually it tips and falls. This is the world you understand. Objects slow down. Everything stops. But there is something in the universe that will never stop spinning. In fact, it has been spinning for billions of years without slowing down even once. Not even a fraction of a percent. It spins so fast that if you could ride on its surface, you would be moving at 1/3 the speed of light. 1/3. The fastest spacecraft humanity has ever built, the Parker Solar Probe, reaches only 163 kilometers per second. This thing spins at 100,000 kilometers per second, and that is not the fastest one we have found. The fastest neutron star we know of rotates 716 times per second. That means in the time it takes your heart to beat once, that star has completed almost 700 full rotations. While you read this sentence, it will have spun more than 10,000 times. In the hour you sleep tonight, it will have rotated 2.5 million times. And tomorrow, and the day after that, and for the next billion years, possibly longer, it will never ever slow down. This is not theory. This is not speculation. Astronomers have observed this. We have measured it. We have data. But before you can understand what it is, you need to understand what it came from, because nothing that spins this fast should exist. The laws of physics say it should be impossible. And yet, here it is. Out there, in the darkness, older than your species, spinning at a speed that would liquefy any normal object instantly. You are about to enter a conversation with the universe about what happens when a star dies. Let us start with something you know. Our sun. Every day, it rises, or appears to. Every day it is the same size in the sky, the same temperature, the same reliable burning ball that has powered life on Earth for 4.6 billion years. The sun is so large that 1.3 million Earths could fit inside it. Most people never truly feel this. They see it in infographics and move on. But sit with it for a moment. The sphere of fire that looks small enough to cover with your thumb, it is so vast that 100 planets like ours would barely register inside it. The sun will burn like this for another 5 billion years. When a star runs out of fuel, it dies. Not all stars die the same way. Smaller stars fade gradually, cooling into dim embers. But large stars at least 20 times more massive than our sun, they die violently. The process is called core collapse. At the end of its life, a massive star has already fused most of its fuel. What remains in the core is iron. Iron does not fuse. Iron is the endpoint. When a star that large runs out of fuel, gravity wins completely. There is nothing left to push back. The core implodes. Not slowly, not gradually. It collapses in about 1 second. The entire core of a star, something that was once millions of kilometers across, compresses inward at a speed so fast that the infalling material reaches 1/4 the speed of light. Electrons are forced into protons. Neutrons begin to form. The pressure becomes so extreme that atoms are crushed to nothing. Everything breaks down into the most fundamental particles. What emerges is a neutron star. A neutron star is a sphere of matter so dense that a teaspoon of its material would weigh as much as Mount Everest. A teaspoon. Not a bucket. Not a swimming pool. A teaspoon of the stuff that makes up a neutron star has the same mass as a small mountain range. If you somehow held a neutron star in your hand, which you could not, because you would be crushed immediately by its gravity, it would weigh more than the entire human race multiplied by billions. But density is not the only extreme thing about a neutron star. There is the spin. When a star collapses, it does not collapse gently. The rotation of the original star does not disappear. It conserves. This is the same principle that makes a figure skater spin faster when she pulls her arms inward. The same conservation of angular momentum. But the collapse is so extreme, so sudden, that this is like taking a spinning wheel and shrinking it to the size of a marble in a fraction of a second. The spin speed increases dramatically, catastrophically. A star that rotated once per month before it collapsed might be spinning thousands of times per second after the collapse is complete. We call these objects pulsars. We call them this because they pulse, because their spin creates a beam of radiation that sweeps across space like the beam from a lighthouse. When that beam points toward Earth, we detect a pulse. When it points away, we detect nothing. The pulses are so regular, some accurate to within a millionth of a second, that when pulsars were first discovered in 1967, scientists actually thought they might be signals from an alien civilization. For weeks, one was literally labeled LGM-1, Little Green Men 1. They were not aliens. They were the remnants of dead stars, spinning faster than anything in the universe should be able to spin, held together only by the most fundamental forces of physics. The first pulsar discovered rotates 1.3 times per second. That seems slow compared to what we know is out there. It seemed slow to the astronomers who found it too. Then we found faster ones. Much faster. The Crab pulsar, the remnant of a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second. The Vela pulsar rotates 11 times per second. These are objects where gravity is so strong and spin is so violent that the entire structure is essentially a nuclear reactor held together by an intense electromagnetic field. But we kept looking, and we kept finding faster ones. In 2020, astronomers discovered a pulsar rotating 716 times per second. Let us sit with this number for a moment, because it is not abstract. At that speed, if a person could somehow stand on the equator of that neutron star, they would need to move at about 117,000 kilometers per second to stay in place. The speed of light is 300,000 kilometers per second. This person would be moving at 1/3 light speed. 1/3. At that velocity, the relativistic effects, the real physics of extreme speed, begin to dominate. Time would slow down for that person relative to a stationary observer. Their mass would increase. The very fabric of space-time would curve around them. But here is what makes this genuinely beyond comprehension. A neutron star, 716 rotations per second, is not even the theoretical limit. Scientists believe some neutron stars could theoretically spin even faster. The equation that describes the maximum speed, it depends on the star's mass, its exact composition, and the strength of the forces inside it suggests there could be objects spinning at 1,000 times per second. Perhaps more. We may not have found the fastest ones yet. They may be out there right now, completing 1,000 full rotations in the time it takes your heart to beat once. And here is the part that should make you feel the weight of cosmic time. These objects have been spinning like this for billions of years. When a pulsar forms, it is spinning incredibly fast, but it is also radiating energy. Electromagnetic radiation and gravitational waves are constantly being emitted, and they carry away a tiny bit of the star's rotational energy. Over time, long time. We are talking billions of years. This causes the spin to slow down, very slowly. An incredibly, almost imperceptibly small amount, but it does slow down. Eventually, the Crab pulsar, spinning 30 times per second, is young. It is only about 950 years old. Already, it has slowed down noticeably since its creation. Eventually, in many billions of years, it will spin once per second, and then once per minute. And then it will be a normal neutron star, no longer detectable as a pulsar. But the fast ones we are discussing, the ones spinning hundreds of times per second, these are old. These are recycled pulsars. They spun fast once, long ago, and then slowed down to something more reasonable. But then, something happened. a companion star entered their orbit. When a binary system is formed, two stars orbiting each other, and one of them is a neutron star, the gravitational pull becomes intense. Material from the larger companion star is drawn toward the neutron star. It falls in a spiral, creating what is called an accretion disk. Gas heats to millions of degrees. It accelerates, and as it crashes onto the neutron star's surface, something happens. It transfers angular momentum. The neutron star begins to spin faster. Not just a little faster, much faster. Astronomers call these recycled or millisecond pulsars, because they have been spun up again by their companion stars. They were old and slow. Now they are young again in terms of rotation, and they will stay at these incredible spin speeds for billions of years more, until the material from their companion star is exhausted. But here is what should hit you. We are not actually at the extreme limit of spin yet. There are objects in the universe that should be spinning faster than anything we have detected. Black holes. Black holes have no substance to them. They are pure space-time distortion. They can spin at nearly the speed of light. There is a black hole called Sagittarius A, located at the center of our Milky Way galaxy, containing the mass of 4 million suns. It is spinning. We do not know exactly how fast, but it is spinning, and neutron stars should be able to approach this limit too. The current record holder that pulsar spinning 716 times per second, it might be the fastest neutron star we have ever found. But it might not be the fastest one that exists. There could be neutron stars out there, invisible to us, rotating at speeds so extreme that the physics describing them exists on the very edge of what we understand about reality itself. Spinning in the darkness, alone, impossibly fast, for billions of years, forever spinning because there is nothing to slow them down. And they will spin this fast for longer than Earth has existed, longer than the human species will likely exist. What does it even mean to spin that fast? What is it like to be matter compressed to a density that should not exist? Shaped into a perfect sphere by gravity, rotating so quickly that the outside is moving at relativistic speeds. The universe is indifferent to what we think is possible. We look at a spinning coin and understand friction. We understand that motion slows down, that order becomes disorder, that everything tends toward stillness. This is entropy. This is how we experience the world. We are animals, built to understand medium speeds, medium temperatures, medium densities. We understand the world at human scale. The neutron star exists outside of this. It is not cruel. It is not angry. It is simply what happens when physics takes the gloves off. When a massive star collapses, there is no mercy in the equations. There is no hesitation. There is only physics. And physics is far stranger and far more extreme than human intuition can grasp. We live inside a universe that contains objects so dense that light itself cannot escape them. We live in a cosmos where certain things will spin forever, at speeds our minds struggle to process. We live on a planet orbiting a star that is in constant nuclear fusion, that is powered by the conversion of 620 million tons of hydrogen into helium every single second. And our star is considered medium-sized, average. The Crab pulsar, the remnant of the explosion observed and recorded by Chinese astronomers in 1054 AD, is still visible today. You can see it with a telescope. A supernova so bright that ancient observers could see it in daylight. It has been nearly 1,000 years, and we are still detecting the debris of that explosion. We are still measuring how fast it spins. We are still learning from it, and it will keep spinning. Long after human civilization is gone, long after the sun has burned out and Earth has been consumed, long after the Milky Way has collided with Andromeda, long after the universe has aged to the point where our sun seems impossibly young, that neutron star will still be spinning. Not quite as fast as it does now, it will have slowed down some. But it will still be there, in the darkness, rotating. There is something almost meditative about this. About knowing that the universe contains things so vast that our largest thoughts are still too small to hold them. Things so old that the age of mountains seems young. Things spinning so fast that speed itself becomes incomprehensible. These objects exist whether we observe them or not, whether we understand them or not, whether we believe they could exist or not. They simply are. And that is perhaps the most important thing to understand. We live in a universe that is far stranger and far more extreme than we assume. Not in a way that is meant to be comforting or spiritual, simply in a way that is true. The equations work. The observations confirm it. The neutron stars spin, and they do not care what we think about it. When you feel small standing under a night sky, and that is a feeling every human should feel, at least once know that you are actually feeling something real. You are intuiting the true scale of things. You are sensing, in some ancient part of your mind, that the universe is beyond your capacity to fully grasp. A neutron star is spinning right now, somewhere in the darkness, at a speed that would vaporize you instantly if you came close. At a density that would crush atoms into nothing, a star that died billions of years ago is still rotating, still moving, still powerful. It will be spinning long after you are gone. And there is a strange kind of peace in that knowledge. Not peace that comes from comfort, but peace that comes from understanding that you are part of something so much larger than yourself that your presence in it becomes almost irrelevant. You are made of the remnants of dead stars. The calcium in your bones came from supernovae. The iron in your blood came from stellar collapse. And the universe that made you is so strange, so vast, so violently physical that your own existence seems almost impossible. But here you are, reading these words, existing in a universe where neutron stars spin 700 times per second and never, ever slow down. The coin on the table will stop spinning. Eventually, friction will slow it down. But out there, in the dark spaces between stars, the real universe is still moving, still spinning, still indifferent to whether you understand it or not. That is enough. That is everything.